Welcome to aminacademy.com. In physics, let us discuss about Kepler's law of planetary motion. Kepler's law of planetary motion, published by Johannes Kepler between 1609 to 1619, describes the orbits of planets around the Sun. The laws modified the heliocentric theory of Nicolaus Copernicus, replacing its circular orbits and epicycles with elliptical trajectories and explaining how planetary velocities vary. The three laws states that the orbit of a planet is an ellipse with the Sun at one of its foci. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. Third one, the square of planet's orbit period is proportional to the cube of the length of semi-major axis of its orbit. The elliptical orbits of planets were indicated by calculation of the orbit of Mars. From this, Kepler inferred that one bodies of the solar system, including those farther away from a sun, also have elliptical orbits. The second law helps to establish that when a planet is closer to the Sun, it travels faster. The third law expresses that the farther a planet is from the Sun, the slower its orbit speed, than vice versa. Isaac Newton showed 1687 that relationship like Kepler's would apply in the solar system as a consequence of his own laws of motion and laws of universal gravitation. Now we'll do detailing about the three laws. Kepler's first law, the law of orbits. According to Kepler's first law, all planets revolve around the Sun in elliptical orbits, having the Sun at one of the foci. The point at which the planet is close to the Sun is equal as perihelion, and the point at which the planet is farther from the Sun known as aphelion. It is the characteristics of an ellipse that the sum of the distance of any planet from two foci is constant. The elliptical orbit of a planet is responsible for the occurrence of seasons. Look at here. This is the elliptical path. Consider out of that one foci is Sun. Here, this planets around the Sun moves like. Second law, Kepler's second law, the law of equal areas. Kepler's second law states that radius vector drawn from the Sun to the planet sweeps out the equal areas in equal interval of time. As the orbit is not circular, the planet kinetic energy is not constant in its path. It has more kinetic energy near the perihelion and less kinetic energy near the aphelion, implies more speed at the perihelion and less speed at the aphelion. If r is the distance of planet from the Sun, the perihelion, that is r minimum, and the aphelion r max is equal the relation r minimum plus r max equal 2a into length of the major axis of an ellipse. Here, look at here. This is the, suppose the Sun is here, this planet around like here, that area swept here is equal to area swept here. For that, here the nearer to this one is speed of the planet is more here. Due to that, this here radius is less, so here the area is it gives some areas. Then same is equal to here, this because it's less distance, here more distance, so it have the equal areas of this and this. Here and here, that equal areas. Using the law of conservation of angular momentum, the law can be verified. At any point of time, the angular momentum can be given as L equal to mr squared omega, and that we can find we can prove that law. Now consider a small area delta A described in a small time interval delta t, and the covered angle is delta theta. Let the radius of the curvature of the path be r, then the length of the r covered is r delta theta. From that we can find the area here and area here, then we can prove that both are equal areas. Kepler's second law can also be stated as the aerial velocity of planet revolving around the sun is elliptical orbit remains constant, which implies the angular momentum of a planet remains constant. As the angular momentum is constant, all planetary motions are planar motions, which is a direct consequence of central forces. Now about third law. Kepler's third law, the law of periods. According to the Kepler's law of periods, the square of the time period of revolution of a planet around the sun in an elliptical orbit is directly proportional to the cube of its semi-major axis. That means square of the time is directly proportional to the cube of its semi-major axis. Shorter the orbit of the planet around the sun, the shorter the time taken to complete one revolution. Using the equation of Newton's law of gravitation and law of motion, Kepler's third law takes a more general form, that is P2 equal 4 pi squared divided by G into M1 plus M2 into A cube, where M1 and M2 are the masses of the two orbiting objects in solar masses, and A is the semi-major axis. In further details, we'll discuss in future videos about these laws and its problem solving. We have done. Please subscribe our YouTube channel.